Hi everybody, time for Ethical Hacking Module 2, TCP/IP Concepts Review. Why do we need to know about networks and TCP/IP? Well, how do you defend something that you don't understand and you don't understand how it works? Regardless, being in ethical hacking and cybersecurity does require knowledge of networks because networks connect everything. And quite often that's where most cybersecurity attacks come from. So we're going to look at TCP/IP, which is the most widely used protocol. It's used almost everywhere I've ever worked. A protocol is an agreed upon method of communication. TCP/IP has TCP, which is Transmission Control Protocol. That's the part that allows a packet to go from one place to the next. IP is the addressing protocol. It is a logical address. So here we have kind of a little bit of the network of the protocol stack. So the network layer represents the physical network pathway in the network interface card. Now in that layer is something called a MAC address. And MAC addresses are theoretically unique amongst the entire world. All the manufacturers got together and decided that they should make sure they didn't duplicate them. However, just like anything else, MAC addresses can be spoofed. So theoretically, this MAC address of my computer is unique. This is a logical address. The logical address will change based on the network you're connected to and what address the DHCP server, in this case, hands out. That's the logical layer. So the internet layer, the IP layer, is the layer that gets you between computers and out of the network. It passes to routers, and routers create networks, and they traverse networks, and that is used to route packets to the correct destination. Now the transport layer is responsible for getting the packet there. TCP is reliable. It verifies packet delivery using handshakes and acknowledgments. UDP just makes sure it tries. Like you're watching this video right now. If there's a few pixels missing or a couple little bits of my voice, it doesn't matter. UDP, it's more important for UDP to be fast and on time than to be accurate. And this layer is the part where the application connects. It's not where the application is. Like for instance, I'm using ScreenPal to record this. And here is my web browser. My web browser connects to the application layer. So the application is actually up here. Well, let's keep going a little bit further into this. So the different types of application layer protocols. So this is the bridge between the network stack. See how things are stacked together? And the application. Oops, kind of lost that. There we go. So the physical layer is what they're referring to here. The physical layer is all the hardware devices, all the wires, the radio waves, the routers, the switches, everything you can see and touch, turn on, turn off. That's the physical layer. It has to be present. The protocol takes over from the physical layer and then allows the operating system to navigate logically through the physical network. Now at the application layer, this is the part that connects to the application. So HTTPS, for instance, there it is. I have Firefox here. And if you look right up here, it has a little lock, as HTTPS. Hypertext Transport Protocol Secure is the most commonly used protocol. HTTP, which is unencrypted, is rarely used anymore. Simple Mail Transport Protocol is used for transmitting information between the post offices. So I send a message to myself on Hotmail, my wncc.edu post office. I send my message to the wncc.edu server. It sends it over to the Hotmail server, and then it puts it in my mailbox. We will be using some of these things, and some of them they weren't. Telnet is inherently insecure. File Transfer Protocol is also inherently insecure. They don't use encryption. Well, SSH has replaced Telnet because it does use encryption. And I think it's SCP is Secure Copy Protocol. That has replaced FTP. Or you would use FTPF, S for secure. TCP is connection oriented. It makes sure that the packet gets from here to there. If you're working, let's say you're going to make a deposit on your bank, and your paycheck comes in at $2,000.25. Well, you want to make sure all those pennies get to your bank when you deposit it. You don't want to have $1,900 get there. So TCP makes sure that each packet gets there accurately. So TCP uses something called a three-way handshake. The client sends what's called a SYN packet. The server receives the SYN packet, and this has a sequence number. The server recognizes the sequence number. Then it sends a packet back, and it increases the SYN number the sequence number it received and sends an ACK +1. Then it sends its own sequence number over to here, to the client. The client receives that. It adds 1 to it for the acknowledgement and sends it back, and the server receives the acknowledgement as acknowledgement equals n + 1. Now they've established a connection, because each direction of the packet exchange has a sequence number to reassemble and disassemble the packets. So, yeah. There are different parts of TCP/IP that can be hacked. This is a look at the different parts of a TCP/IP segment header. There's a source port, destination port, sequence number, acknowledgement number. Those are the synchronization numbers. These are the ones we'll be working with the most. Source port, destination port, sequence number, acknowledgement number. The SYN flag acknowledges the beginning, acknowledges reset, allows us to reset. These two will be using the most as we create our own packets. So the initial sequence number is a random number that establishes the beginning sequence number of packets from one to the other, so that when the other receives the packet, it knows how to reassemble it. A port is a logical component of the connection. For example, when you're using your web browser to go someplace, you're using port 443. That identifies the service, typically. If all you have on that server is a web server, you really don't need any other ports open. We're going to do some port scanning and network scanning and see things that are open that shouldn't be. The rule of thumb in security is have no more access than necessary to get the job done. Same thing goes with servers. No more ports or services than necessary. Okay, we're going to skip that. This just gives a bunch of the different ports and what they're used for. UDP is fast but unreliable. Again, that is Netflix, Prime. When you're watching this video, it's a connectionless protocol. It just gets there as best it can, and that's all it needs. If there's a few bits missing from the image or my voice or the video, doesn't matter. The important part is that it gets there fairly quickly, or very quickly. ICMP is a network troubleshooting protocol. Typically we use ping quite often, and we use traceroute. Those are two commands, or applications actually, that use ICMP to troubleshoot connections. So we use ping to make sure that we have a connection to the network. Let's see here, where's my ping? There we go. If we ping google.com, we're sending ICMP packets to Google. The packets come back. We know we have internet connectivity. It takes 7 milliseconds to go from here to the nearest Google server and back again. 7 milliseconds, well, there's 1,000 milliseconds in a second, so that's pretty darn fast. We're not going to worry about the ICMP codes. Let's see. All right. So Class C networks are divided up into 3 basic types of networks. Here is the Class A network. The first address is 1 to 126. You can have 126 networks with 16 million hosts. Well, we don't really use class A, B, and C anymore because who needs 16 million hosts on a network? We use what's called classless subnetting. But this gives you the general range of IP addresses that are available. An IP address is composed of 4 bytes. It's called an octet. Let's see, class B, we're not interested in that. There we go. So here is our IP address translated into binary. So it goes 1, 2, 4, 8, 16, 32, 64, 128. So there's 1 over here. That means it's 1 in the 128th part. And that's what you do. Everywhere there's a 1, that means there's a value there. Here it's 120, 255, because all of them are filled up, 255, 255 by 0. So this first part is what's called the subnet mask. It masks out the network. If I am transmitting a piece of information from my host to another and this matches, I know that I'm on the same network. This is unique for each device on that network. If this does not match where I'm sending the packet, say I'm going to Google, well, then it goes to the default gateway. So either the address is on the network, which means that the other address matches this, but it's unique in this piece, or it doesn't. If this doesn't match, out the default gateway it goes to the router, which hopefully knows how to send it to its destination. We'll work with all these pieces as we go through the class. Now, CIDR notation is just a short way of saying we could do it like this. Those are the same thing. This designates a subnet mask. There's 12 bits. Sorry, there's 8 bits in a segment. And so 8, 8, 8. 3 times 8 is 24. There's 8 bits in each of those octets. And this gives you the CIDR addressing. So we don't need a million hosts because we can split the addresses available into smaller ranges. All right, so how do you plan IP address assignments? Well, that's a good question. Typically, you set static IP addresses for servers and routers and switches if they're managed switches. Each computer must have the IP address of its gateway because it needs to know where to send the packet if it is not part of the if it's not part of the network. So, for instance, on my network, if I ping 192.168.9.1, that's my local router. This part matches my network subnet. If I ping Google, it's going to go out the default gateway because this part does not match. This part does not match my network, so it sends it automatically to the router. So your computer determines, is it part of the network? If it is, it sends it directly. If it's not part of the network, it sends it to the default gateway, which happens to be this address. IP version 6 is coming along. It's been, I think, 10 years or so. It's been starting to be implemented. We don't use it a lot yet in many businesses because IP version 4 works pretty well. IP version 4, which is what we're currently using and what we'll be doing most with in this class, was not designed with security. IP version 6 was designed with security, and it has a lot more available addresses. Okay, I think, yeah, we're not going to go through binary. It's handy to know binary, but that's not something we need to know. Okay. That should take care of our introduction to ethical hacking. I mean, our introduction to TCP/IP. There's a couple other pieces in here that we may look at later on, but we're done for now.